Okay, everybody, welcome to the next iteration of the Cambridge Cheminformatics meeting. Just here today and online, not multi-site this time, so thank you very much for attending. We have three very interesting talks today. One of them is on progress towards InChI keys and InChIs for molecular identification, presented by Professor Jonathan Goodman and Ian here at CCDC. And then we also have Javier from Pharmacelera talking about huge chemical space exploration with their 3D hydrophobic profiles. And then lastly, we also have Will from here at the University of Cambridge, a PhD student, talking about fragment-based hit discovery. So just before we get started, a couple of things. Firstly, we'll follow the meeting today with a pub trip, as we always do. So please come along to the Alma. We'll be going about 6 o'clock. And we also want to thank the CCDC for hosting graciously, as always. So on that note, just a couple of things. Fire safety. So you all signed in today, so please also sign out when you leave the building. There was a fire alarm, I'm assuming at 12 today, so we're not expecting one. So if you do hear one, then please vacate the building. There are some open vacancies at the CCDC. So if you're interested, you can find out more online or talk to someone from the CCDC here. And also we have a save the date for the RSC CCAG 6th Artificial Intelligence and Chemistry meeting. So that'll be on the 4th and 5th of September. So just keep that in mind. And if you're interested more in what the RSCs do with CCAG, then you can have a look here. So let's stick to time and have our first presenters, which is Jonathan Goodman and Ian. So let's get started. Do this one first. Yeah. It's the other one.
So your slides are just before the reading.
Okay, so these ones. Yeah. All right, I'll leave it over to you. Thank you.
Thank you very much. Thank you for the invitation. So I was asked to talk about the InChI. My title, of course, comes from ChatGPT. What's a good title for a talk on InChI? And that's what it suggests. So this morning I logged on to ChatGPT to say, what should I say in my talk? And it said ChatGPT is at maximum capacity. So unfortunately, I have to make up some words myself. So I apologize for this. Also in 10 minutes, Ian Bruno is going to take over, whether or not I've finished. So, so what is the InChI? Well, I mean, my fundamental theorem of chemistry is all molecules are interesting. And that's a real problem because all molecules are so different, so diverse, and so intrinsically interesting. Now, here are some representations of molecules I've studied. The most interesting ones with Dominic Wright, my colleague in the department. And every single one of these molecules is fascinating. I could talk for hours on each of them. But if we have an identifier, if we have some way of reducing these molecules to a string we can easily search, then all sorts of problems arise because we have to decide what a molecule is. This is a non-trivial question. Actually, for the top two, it's probably fairly, or the top line is fairly straightforward. For the bottom left, each of these is two different molecules for reasons too obvious to mention. And whatever is happening on the right-hand one, I mean, that really is a molecule. Ideas of bonding and so on are just a bit tricky here. I don't think it's in the crystallographic database, at least not in that form. So how can we have an identifier which covers all of these different things? It's not by any means trivial. Even if we stick to organic chemistry, then it's not trivial to create an identifier. So just some simple examples of organic chemistry. Orthoxylene, great molecule. Of course, we can draw it in two different ways because where are the double bonds going to be? Well, I mean, you can draw it in lots of different ways, but if you localize the double bonds, which people tend to do, then we have two quite different representations of orthoxylene. They ought to have the same name, and we can call them both orthoxylene. But if you begin from that diagram, you should end up with the same name. Similarly, nicotine, go from that structure to a name. Ideally do this in a computational way. Of course, for this to work, you need to be able to draw things in a consistent way. There are two wonderful papers by Jonathan Brecker in Pure and Applied Chemistry, which tell you just how to draw all molecules. And every serious chemist will have read these papers and memorized them. Yeah? Good. But if you're one of the tiny minority who hasn't memorized all of these, then you might not draw things in exactly the right way, but you still want the same identifier for your molecules, even if you haven't drawn them quite right. And even if you haven't named them quite right, because of course you're looking at this and thinking, oh, xylene, that O should be italic, this circle should be tilted slightly to the right. So I apologize for that, there is an error here. And similarly, nicotine, you're looking at that and thinking, that's not nicotine. Nicotine is a single enantiomer. This representation is probably racemic, or maybe it's a scalemic mixture, or maybe it's a single enantiomer, we just don't know which one. So the name doesn't correspond to structure, and I apologize about that. But so even for organic chemistry, it's really quite tricky to get an identifier which is unique for a single structure. Very, very hard, but not impossible. The answer, as you might guess from the title, is the InChI. Now, the InChI is a family of different technologies. The center of this bullseye, the InChI itself, this is designed mainly for organic molecules. It was a program written by Dmitry Cheskosai, who is actually a mass spectrometrist. Now, if you're a mass spectrometrist, you have a slightly different view of molecules to organic chemists or people in other parts of chemistry. So if you're going to design an identifier, you have to make decisions about when you decide two molecules are different and when you decide they're the same. Dmitry made excellent decisions. If you look at them in detail, one could certainly argue you could have done that in a different way, and they could have been done in a different way, but he's made decisions. They are good decisions and useful decisions and encoded in the InChI. Just to annoy John, I call this a representifier instead of an identifier, because is the InChI, it's certainly an identifier. Is it also a representation? Well, if it's a representation, you should be able to go from the InChI to everything about the molecule. If it's an identifier, it'll just be unique for that molecule. Well, it's not a representation, but it has some properties of representation. I think it's halfway there, so I will call it a representifier, but definitely an identifier. So and once you have the InChI, which works well for organic molecules, you can build up to organometallics, which are impossibly difficult, but Ian's going to explain them, so that's okay. And other things, reactions, variable structure, very large molecules, polymers, reactions, mixtures, all of these can be built on the core InChI technology. So how does that work? Well, the key idea of the InChI is it's canonical as a canonical identifier. So every molecule has one InChI, and if you have an InChI, there's only one molecule which corresponds to this. And this might not sound that difficult. I mean, you can draw a molecule, you can write down something which describes it. Surely you can do something which will work for everything. Well, it's actually quite easy to do something which works for lots of things, but there's a big difference between lots of stuff and everything. And this is what InChI tries to solve. So I have an example of an InChI which is hidden below the bottom of the screen. But so propane has an InChI. Now, propane, I mean, many of you will use smiles. The smiles for propane is just capital T, capital T, capital C. A great way of describing propane. The InChI is better because it's longer. So the InChI for propane isn't just CCC. It begins by telling you it's the InChI, it tells you it's a version 1 standard InChI, then it has a molecular formula, then it has a connectivity with a unique numbering, and then it tells you where all the hydrogens are. So it's a fairly long string. Propane, in a way, isn't an ideal example because as you get to more complex molecules, the InChI will grow, but not that much. But if you think the InChI is too long, don't worry. You can compress it into the InChI key. Here is the compressed version, which, okay, it's not that compressed in this particular case. But however complicated the molecule, the InChI key is always exactly this number of characters, which is totally convenient for building up databases and so on. Because the InChI key is a precise number of characters and you calculate how many different InChI keys there are, you can show that there must be more than one InChI key for, the InChI keys are not unique. There will be several different molecules with the same InChI key. The Sale theorem of chemistry is that everything is water because every possible InChI key can just be a cluster of water, which is true but not terribly useful. There are enough InChI keys for this to be a really useful identifier. So this works well for propane, and for more complicated molecules like pentene 2-ol, this works in a similar sort of way. Again, we have the formula, then we have the connectivity, unique numbering, then where the hydrogens are, and the bits on the right-hand side show that we've got show what the stereochemistry is and show what the double bond is. So actually, if you lose the right-hand end of this, you'd still have valid inches. But because of the right-hand bit, and there's still a valid inch, we just don't know whether it's E or Z. If we cut off a bit more, we don't know whether it's E or Z or R or S, but it's still a valid molecule. And if you just get down to molecular formula, this is a valid InChI telling you only what the molecular formula is. So this works rather neatly, and the way of defining the numbers uniquely works extremely well. This layered construction is a very effective way of deciding how molecules should work, and the InChI key hashes the different layers slightly differently. So the stereochemistry comes in the final stage of the hash. So the InChI is not designed to be human readable, but you can do this, just in the formula, okay. The InChI key really isn't human readable, except if you see Ufer-Euser. This means no stereochemistry, no double bond geometry, no charge, basically boring. So this is what the InChI is, and because it's unique, it can answer questions which are not easy to answer with SMILES or other things. I mean, SMILES is an excellent answer to slightly different questions. If you choose the right question, InChI is definitely better than SMILES. And yes, the reverse is also true. So for this molecule at the top right, I should have saved this for an exam question. How many stereoisomers are there of that molecule? It takes a certain amount of thought, but one thing is to write down everything, calculate the InChI, and the number of distinct inches is the number of stereoisomers. So molecular identifier is unique, interchangeable, ordered molecular collections. If two different people have the same molecule, they will have the same InChI, even though they haven't talked directly to each other. And it's used very widely. It's used in PubChem, Axis, CAS, many journals. You can make your own using ChemDraw or ChemSketch or many other free programs, or you can download the original code from the InChI Trust website or from GitHub fairly soon, or possibly now. Anyway, GitHub before too long. And so this is everything you need to know about the InChI. And it is perfect almost. I mean, because the difference between it working for a lot of things and working for everything, I mean, it works for lots and lots of stuff, but maybe we ought to test it. Let's try it on PubChem. 100 million of my favorite molecules. How well does InChI work? Well, perfectly, pretty much. So almost nothing goes wrong, but if you're testing it on 100 million molecules, there are one or two minor wrinkles. So if you were thinking it's easy to do this, anyone can write down an algorithm to generate an identifier for a molecule. Well, you can do one pretty easily, which will work most of the time. Test it on 100 million molecules. Are you going to be 100% right, or are you going to be not quite right? InChI version 1.05 had a problem with this molecule. How many stereoisomers are being represented here? I leave this as an example as a problem for the audience. If you use version 1.06, the latest version, it will tell you the right answer, but not for the molecule on the right if you run it on Windows, but fine on Linux machines. So there's another message here, and this molecule just be absolutely straightforward with you. This is one of my favorite PubChem molecules. The right-hand side is how it's represented in PubChem. The left-hand side is a different way of representing the same thing. It's not immediately obvious these two are the same molecule, but they are. And there is a numbering instability for InChI for this particular example, but for almost nothing else. And soon we'll fix this. And so the InChI is wonderful. It describes all organic molecules uniquely. It is an excellent identifier. It's even pretty good at organometallics, so they're really difficult, aren't they?
Thank you. So I'm just going to talk through a little bit here how we at the CCDC have been taking advantage of InChIs to do some of the things that Jonathan's just outlined. Many of you will know the Cambridge Structural Database has over 1 million small molecule crystal structures of organics and those organometallics, but it's also a rich source of information that is relevant to a range of different domains.
areas such as drugs, food additives, pesticides. We can think about its relevance to general chemistry, relevance to biology, inorganics and materials, and connection between crystallography and analytical data. And in all those different areas, there are lots of different data resources. So we want to be able to link from the CSD to those data sources. And this is something that we have been sort of working on over a number of years, and InChI has been instrumental in helping us to establish those links. Now, Jonathan's essentially done this slide. Why InChI? It allows us to sort of not worry about different but equivalent representations. It also has this layering aspect, which will become important as I go on. Because you think it'd be straightforward. Jonathan obviously described it to be straightforward, and on the whole it is. But when you're starting with a crystal structure, it's not necessarily so straightforward. The data that comes into the CCDC will almost certainly include atomic coordinates, and it usually includes an indication of which atoms the crystallographer thinks are bonded together. What it doesn't have is the bond type. What it might also have is crystallographic artifacts such as disorder. There may be atoms missing, or crystallographers will also squeeze out these pesky solvent molecules that are just getting in the way from getting a good model of the main molecule that they're looking at. It's got better these days as far as hydrogen is concerned, but certainly in early structures, those were very difficult for the crystallographer to replace. These days, they tend to be calculated. And so we have to deal with all this when structures come into the CCDC. And one of the most important tasks that our editorial team do is make sure that we have a validated 2D representation of the substance that has been studied. And that will include the bond types, we'll make sure the number of hydrogen atoms is correct, and we'll make sure all the components in a particular sample are represented. And we use the 3D input to help us generate that, but then we make sure that the chemistry is mapped back onto the 3D structure that is stored in the database. So we have here two sort of representations of the same structure, which don't both contain all of the information we need, because although the diagram is accurately describing the chemistry, it doesn't actually represent the stereochemistry, but the stereochemistry is nice and precisely represented in the 3D model. So a CSD represent entry is a mapping of the 2D and onto the 3D, and it's that we use when we want to generate reliable entries for CSD entries. We want to use the best of the 2D, the best of the 3D. And so what we do is that we generate InChIs for the 2D components in the 2D diagram, and we tell InChI, trust our hydrogens. When it comes to then what we do is generate a 3D InChI, and there we allow InChI to sort of work out the stereochemistry for us, adding hydrogens if needed. And then we look at the 2D and the 3D, and if the connectivity layer, which is the bit highlighted in green, is the same for both the 2D and the 3D, we know we can trust this 3D InChI generated from a 3D model that may be imperfect. If those connectivity layers didn't match, then we'd ignore that 3D InChI and just go with the 2D, which means sometimes we'll get an InChI, which as Jonathan was saying, that represents the connectivity, may not represent the stereochemistry, but we don't reliably know what it is. So having done this, what sort of insights can we generate using InChI looking into the CSD? So here I'm just giving you a little bit of a background into how the Cambridge Structural Database is structured. From the very beginning, we grouped together different determinations of the same chemical substance. So that would mean if I've got one molecule that's the same as another, these all get grouped into what we call CSD families. So these might be different determinations done on different samples, or the same sample under different conditions. It might be a re-refinement of the same data. What we don't group together are entries where you'll find the same molecule in a structure, but with maybe different co-formers, maybe solvates, other co-formers, etc. Ref code families are great if you're thinking as a crystallographer and want to group things together because they're polymorphic. They're not so great if you're a chemist. So can we use InChI to generate some novel groupings of CSD entries? So this chart that I'm showing you here, each blue dot is essentially an InChI. Down the side is the number of CSD ref code families that InChI appears in. Along the bottom, it's just the size of the molecule to give some form of discrimination. There's a question there. Anyone want to guess the small molecule that appears in the greatest number of CSD families? Anyone want to guess the smallest charged entity? Yeah, water, absolutely. And InChI allows us to very quickly find out that out of a subset of CSD entries, exactly how many are hydrates. Yeah, fantastic to be able to answer that so quickly. Chloride is the smallest one when it comes to the counter ion. This is a redrawing of that chart, taking away those small molecules and the sort of smaller ref code families here. And we start to discover these common coformers that appear alongside quite a lot of different other main entities. And you sort of look at the paper titles and they feature in structures, studies of hydrogen bonding and the like. Lots of work gone into crown ethers, 297 articles over 70 years. And then this binaphthalene turned up quite a lot and seems to be implicated in a lot of enantioselective syntheses. It was only really by using this InChI-based grouping of the CSD that we were able to see these. And then we also get some very interesting molecules here. So here we have a beta cyclodextrin inclusion complexes, which over a period of from 1981 to 2022 has been crystallized with over 210 other molecular components flashing before you on the screen there. Quite a body of work that's been involved in. And then the second example I want to show here is pseudo-rotaxanes. And now these are notoriously difficult to sort of identify using conventional substructure-based methods. With InChI, we can sort of identify groups of these where the same cucurbit has been used in these particular types of interconnected molecules. So there's more work we want to do at the CCDC using InChI. Coming soon, we're going to be releasing in our CSD Python API for the first time the ability for other people to be able to access InChIs for the CSD and generate their own. We want to be able to build on that to enhance our web services, search services using that, and think about offering alternative ways of navigating through chemistry space. We use it to link to even more data resources. My colleague David is currently exploring with Egon Winnehagen how we can link to information in Wikidata. We're looking to extend coverage of other resources such as PubChem. We're using them in a project called BioChemGraph, which I'll say a little bit more about in a minute. But we're also supporting the development of those pesky organometallics that Jonathan was referring to. So just a very quick word on organometallics. We exclude those when we're generating reliable InChIs because at the moment the standard behavior is to disconnect bonds to the metal and not reconnect them. Now, sometimes organic chemists say, well, do you really need to reconnect them? And organometallic chemists will say, oh, yes, you do. So here's an example where you've got three ligands in the organometallic sense around the coordinating to a particular metal in different ways. In one example, one ligand is bidentate, for the other it's monodibentate, and vice versa for one of the others. So it really matters that we reliably represent the metal coordination. But after more than 10 years of discussion, I think we got to the point where he said InChI probably actually does have the solution to it already in it, and there's now work moving forward to sort of establish more reliable InChIs for organometallics. One of the additional challenges there is working out the additional stereochemistry that you'll find in around metal coordination centers. And then the final thing to mention is BioChemGraph. It's a project we're involved in with the EBI to look at linking between the CSD and biological resources. InChI is going to be very much the foundation for that. This project has also provided some of the funding that has allowed us to do some of the recent work to generate these reliable InChIs on a sustainable basis. So just to conclude, InChI is great for linking across chemistry resources, for surfacing connections within the database, and we've also used it to also look at the consistency of our own collection as well. And the future looks bright, particularly as the work for metal organics progresses. I want to acknowledge, as well as leading SLC, my CCDC colleagues, Francis Atkinson, who's now moved on, and David Lowe, who've done a lot of the data wrangling. And then our developers who have been recently working on this, Simon, Lin, Sean, and Nigel, but also the wider InChI community who have all contributed to making InChI what it is today. If you'd like to get involved, speaking on behalf as Jonathan as Secretary of the IUPAC Subcommittee on InChI, myself as Secretary of the InChI Trust, there are great opportunities to do so. Jonathan mentioned the source code moving to GitHub. That process is underway. We're lucky to be benefiting from software development contributions at the Aachen University, which will help get us to a point where we've got the source code out there for people to contribute to. So that, I think, a little bit over, but that is our presentation. Thank you very much.
Thank you very much, both Jonathan and Ian. Do we have any questions in the audience? Okay, a couple.
Also pesky organometallics. I mean, this is what project which is going on at Arkin is looking at, because when are two molecules the same, when are they different, will you get different answers from different organometallic chemists? Just as for the organic chemistry, there are a few areas of organic chemistry where people will argue about whether two molecules are the same or different. Not all that many areas. In organometallic chemistry, there are lots more areas. But if we can make a decision, not everyone will agree with it, but it will be a useful thing because it is a standard which provides a differentiation, which at least people know what it is, even if they have a better way themselves.
I think the working group has established the kind of rules and conventions that define in principle what is the same and what is different. One of the next challenges is thinking about the representation formats that are out there and how consistently they are used by the wider community, so that people are actually providing stuff that can be consistently interpreted, whatever they represent. Oh dear.
Yes. Yes. So read the paper. No, the paper is very good. In fact, but the paper just has a sample of the problems. There are one or two more. So actually, the technical release notes, the InChI version 1.06, has a list of things which, and on the whole, I mean, whilst all molecules are interesting, these are less interesting molecules. So, which. Oh yes, but I'm not sure that's an error. It's just this is a molecule which you draw in a mol file, and then some people think they mean one thing, and actually you're telling the mol file something you don't realize you're telling. Well, John realizes what he's telling the mol file, but not everyone knows what they're telling it. So the InChI is correct, just not what you expect. And I think this is a no. You think?
But was it M or P by that?
Hmm?
So you showed by that.
Okay. Yeah. Oh right. Okay.
No, a top has.
Right.
And they're so rare, but of course by that is the example, right?
Yeah. Okay, that's interesting. Yeah, that's an interesting one.
It was a nice example.
Yeah. And I think what that illustrates is the challenge whenever putting these presentations to find the perfect example. No such thing exists. There's always something interesting about it, which means that yeah.
One last question online. This might be a quick answer. Can you talk about the possibility of collisions in InChI fingerprints?
Well, in InChI keys, you can calculate how many InChI keys there are. You can calculate how many possible molecules there are many more molecules than there are InChI keys. Therefore, there are lots of collisions. If we made the InChI key 100 times longer, then there would still be collisions. You can't get rid of this if you're having a compressed key. However, the number is kind of useful. So in PubChem, 100 million, no collisions. I mean, perhaps we were. And we think we weren't terribly lucky because you can work out the probability of collisions in a 100 million database, and it's pretty low. And as it turns out, there were none. But this is actually terribly important because some people think you're unlikely to get collisions, but actually you should just be slightly worried. Collisions are possible, check for this, or your software isn't perfect. But the rate of collisions is very low.
Even theoretically, I think.
Well, both theoretically and practically, you get the same number, but reassuringly.
Perfect. Thanks very much. Another round of applause, please.
Great. Thanks for having me. I'm William. I'm finishing my PhD in the Alpha Lease group in the Cavendish. Today, I'll be talking about some recent work I've done on fragment-based hit discovery So it starts off with a very quick intro to fragment-based drug discovery. This is kind of a particular approach that focuses on crystallizing very, very small molecules called fragments. The idea would be that they bind to different bits of the binding site, and combining the structural information from these fragments, you can kind of hopefully get to a more potent compound. And that get to a more potent compound bit is the hard part. Here are some of the strategies that have typical ones. It's a real craft. So, for example, if there's a bit of the binding site that's not been occupied, you can try to kind of grow into it. Or if you have two fragments that are near each other, or they have some kind of overlap, you can try to connect them. I wish it looks as easy as it is. It's actually quite frustrating sometimes. And I think importantly, there's no real substitute to this trial and error, apart from, docking the merged compound at the end. But choosing which pair to merge, what kind of linker is the best kind, it's still mostly a craft at the moment. So this work is kind of exploring a very different way of approaching this problem. So up there in this box, this is the traditional approach where human expertise kind of does most of the heavy lifting. And today I'll be introducing a more data-driven approach, which is treating the structures from a fragment screen as a distribution that we can learn from, specifically a distribution of pharmacophores, and can use that learned distribution as a scoring function. So I'll elaborate on that. So first of all, pharmacophores, if no one here has heard of them before, they're just a very useful way of coarse graining a molecule. So instead of this molecule here being a very particular graph, particular atoms, we can kind of take our glasses off and vaguely, this is a couple of aromatic groups with some donors over there and acceptors over here. And kind of the big point of doing this is that it makes it easier to explore new structures that if I take another molecule, could be a totally different graph, different atom types. If the same pharmacophores are in roughly the same place, I expect it to kind of bind similarly, or at least bind. So if I have a bunch of molecules, well, in this case, specifically fragment structures, and I turn them all to pharmacophores, I would expect to see something like this in 3D, that the donors, for example, they would all end up in a similar place, having a similar interaction to a particular residue. The aromatic groups would be in a similar place doing pi stacking. And if there are some irrelevant interactions, then you don't really see a dense overlap of where the pharmacophores are, and we can ignore those interactions. And this is obviously borrowing a lot of intuition from pharmacophore modeling. This is kind of a separate strand of cheminformatics. And the only reason why I can even attempt something like this is that crystallography the throughput has really increased recently. So this is a particular protein. I think the fragment screen came out sometime early last year. There's 200 fragment structures for this, which is, if you were to naively look at each pair, that's 200 squared pairs. It's 40,000 pairs of fragments, and that's way too much to evaluate. So with this kind of data, there's actually enough data points to try and deal with this in a data-driven way, thinking about distributions instead of separate instances. So that's quite abstract. What distribution am I actually trying to model here? So specifically, I will try to model the pairwise distances between different kind of pharmacophores. So, for example, this histogram here would be the distances between a donor and acceptor group. And I would measure or count all the different distances from all of my fragment structures. And for example, I would see there's a pair that's quite close, 2 to 3 angstroms. There'd be one that's 8 angstroms apart, 12 angstroms apart, depending on the shape of the binding site, where the structures end up. And if I can learn this distribution, I can learn which pairwise distances have a higher density than others, then I can grab a totally new molecule, a ligand, a potential ligand, and I can compare the pharmacophore distances in this molecule to my learned distribution. If it has a distance of 6 angstroms, then I know this is probably not going to fit anywhere, at least according to the information the fragment screen is telling. So this kind of approach, this learned scoring function, I call this fragment ensemble scoring. So that's all good in practice, in theory. I'll show some kind of results on how this approach looks like. So in this particular example, I'm looking at the protease of COVID-19. The reason for choosing this target is that there is a published fragment database about a set of fragment structures, 23 of them, quite decent. And more importantly, there is an published data of different designs for inhibitors against this target from a campaign called COVID Moonshot. I think they got all the way to the preclinical stage, awesome science. And this campaign, importantly, it started off exactly from these fragment structures. So I can kind of retrospectively look at the structures from the more initial stage, going from a fragment, those fragment structures, their initial hits. But if they had fresco, the fragment's almost growing, what would their hit rate have been, potentially? So looking at the data, there's almost 1,000 different structures there, 1,000 different compounds. And we actually see quite a good hit rate. And I don't want to dwell on, is it better than docking or whatever. To me, that's not the point. The point here is that I have a relatively simple model, or just knows pharmacophores, the distances between them from 23 fragment structures, and is actually correlating with binding affinity. And I think was surprising to me the first time I saw it. I think this is pretty awesome. I could have stopped here or done more optimization, done more computational benchmark, but we decided more convincing evidence would be to go prospectively, actually go try to synthesize the molecules and test if it works. So prospectively, we decided to look at 2 different protein targets related to COVID-19 for antiviral inhibitor design. So the protease here, that's the target from just now. And MAC1, that's the compound from before that I showed that had loads of fragments. And the reason there's only 100 here, I think quite a lot of the fragment hits were covalent. I'm only specifically looking at non-covalent fragment hits because I think the type of interactions are different. And I just want to model non-covalent ones for now, at least. The workflow I use for this, for trying out my approach, this is how it looks. So I would train my distribution, my pharmacophore distribution learning model on the fragment protein complexes for each protein separately. And at the same time, I would featurize enamine real. At the time when I did this, there was only 1 billion molecules. There's a published data set of conformers for enamine real, about 1 billion conformers. So I converted all of them into pharmacophores, calculated the pairwise distance distributions for those compounds, and I ranked all of those. I did the virtual screen and ranked those compounds by the probability. And once I'd done that, then I had to choose which compounds to synthesize. So I ran a filtering for physical chemical properties, and I did a clustering method, and it chose chose molecules from the most populous clusters. I've maximized the diversity of the molecules I picked. Now, show some of the results of that. So first of all, for the protease, these are the kind of compounds this approach seems to like. So those are the compounds on the right. These are the compounds chosen by the model. So going into kind of pharmacophore mode, it does seem to be vaguely 2 aromatic groups that are connected by an amide-ish kind of functional group. And there are a few of the fragments that do actually exhibit this kind of structure. And the other fragments also tend to have 1 aromatic group and looking at the 3D structures, they would be bound at either the left-hand side or the right-hand side of these groups. So that's the kind of interaction, vaguely speaking, that seems to be picked up by the model. And screening all of enemy real, that's the kind of, that's a scaffold it seems to like. And are any of these actually any good? Well, 1 out of 38 of them actually has decent activity. And just to check that it's not a false positive, some weird artifact, we actually did follow up, just relatively simple, just varying the structure, adding some groups to the kind of left-hand side and right-hand side of this compound. And it's not that all of these are inactive. There is some definitely reliable structure-activity relationship going on, which confirms that this compound isn't a singleton. And that's quite reassuring. And for the second target, SMAC1, this compound has a natural substrate, which is adenosine. And if we looked at the compounds, again, from screening all of enamine real, the compounds that the model ended up liking, they also tend to have adenosine-like kind of scaffolds, which is really amazing to me. Now, to be fair, some of the fragment hits also are adenosine-like. This case, 3 or 4 of them out of the 100 plus the fragment hits actually had this structure. But I was very happy to see that this relatively simple approach can actually narrow down exactly to this kind of scaffold screening enemy real. So again, are there any of these molecules actually any good? Well, there's one of them that is weakly active, but we also managed to get crystal structures for this compound. And for a few other ones, we also got crystal structures, but no hit on the assay front. If we actually look at the crystal structure, unsurprisingly, I guess this adenosine-ish scaffold, the pharmacophores of this compound line up with the pharmacophores from the fragment screen. This is what we expected, and that's what's happened. Very good to see. And as before, just to check that it's not a singleton, it's not a false positive, we did some perturbations of the chemical structure, and we reliably see the structure, the activity going up or down with minor changes. So it's not the fluke that this one works and any small change to it doesn't work. So that's kind of the results of our screening. And the kind of implications, I mean, this approach that I developed here is quite novel. It's not optimized at all. I'm sure there are many, many ways where this could have been improved. For example, we only looked at pairwise distances. I'm sure you could do free body, end body, kind of more sophisticated modeling of the geometry of the distribution of these pharmacophores. We only looked at fragment structures, didn't consider kind of having a loop of obtaining ligand structures, refining the model, that could have facilitated us growing fragments, kind of. We specifically didn't look at combining this with docking in any way. This was an intentional choice of separating out any confounding factors. Or did this actually work because we ran docking? Probably it would have been better if we actually want to implement this for real. But I guess apart from the specifics of what I did here, and the very general idea that we can, well, now that we have this high throughput structural biology and getting loads and loads of structures, we can actually do this kind of analysis of correlating structures, say, whether it's binding towards the same target or more biology focused kind of science, that instead of looking at structures one by one as separate instances, we can leverage correlations from lots of structures against the same target. I think there are lots of different problems that can be tackled in this kind of spirit. And this last kind of throwaway data point here, bullet point here, which is that the approach I use is very specific to that target. It's very specific for one fragment screen. And I'm sure you could use, well, hopefully there could be a deep learning approach where you can leverage, like do this for multiple targets, transfer learn data from different binding structures and use it for unseen structures, and that'd be fantastic. That's kind of it. I'll end here. I'll be happy to answer more questions. There should be a slide here for acknowledging my collaborators. The teams have disappeared. I couldn't have done this without lots of great experimental collaborators from the Weizmann Institute, from UCSF, from Oxford, running the assays, the crystallography, and my supervisor for making all of this happen. Thank you.
Very much, Will. Turn this microphone back on. I must say it's really nice to actually see some prospective validation in these kind of approaches, which is often sorely lacking. Do we have any questions from the audience? We have a couple online, so we'll go there first. Okay, so we have one that says, very interesting. How did you represent the fragment learning to pass to the unsupervised learning approach?
So let me go back to the slides. So what is being learned is this histogram of pairwise synthesis. So let me think. So for each pair of pharmacophores, there will be a different distribution. This in particular is the donor acceptor distribution. I would have a totally different distribution for the distances between two aromatic groups, for acceptor aromatic. So in this case, enumerating the pairs, I have 6 different pairwise distance distributions that need to be learned. And that was a choice I made in terms of which pharmacophores I want to include. I could have added, for example, hydrophobic interactions. Could have tried to do more charged pharmacophores. I think there's a rich literature in how to define pharmacophores and what counts, what doesn't count. In this case, I'm only looking at donor, acceptor, and aromatic pharmacophores. And the distributions I'm learning are the pairwise distributions between these pharmacophores from different fragments. So this would be a distribution. I would fit a curve to it, and that curve is the model, essentially. That curve describes the probability of a pairwise distance of pharmacophores to match that of the fragment screen. Hope that answers the question.
Perfect.
Ask another one.
Yeah.
Is there any sort of distribution of which pharmacophores occur in a molecule, or are they, or do they all occur with equal probability?
Yeah, so when the molecule has multiple pharmacophores, right, so that itself is a distribution. And in this case, that would correspond to multiple points on this curve. So the molecule down here, right, for example, that could have 3 different points. And in this case, I take the mean of those values. But otherwise, you would have, you could cheat the system with a very big molecule with loads of distances. And just take the max, then it would get exploited. So I just take the mean here to make sure I keep the number of pharmacophores to a reasonable number. Yeah.
We have another question online, which says, is there a minimum number of fragments needed for this method to be successful?
Good question. I mean, the 2 targets I looked at, one is 23 fragments, which I understand is quite a good number. Maybe depending on the target, depending on your fragment library, you might get less. I haven't explored anything less than that, or I suppose hopefully 10 fragment hits. And yeah, but hopefully this will become a more common occurrence. I'm not super aware of how many fragment hits, say, Aztecs or more internal proprietary data sets, that how dense their hit rate is. Presumably quite good.
Yeah, thanks. And consequently, you also answered someone else's question with another one that you answered. And I was just wondering, do you treat fragments that overlap slightly differently at all?
No. So if fragments do overlap, or I guess in particular, if pharmacophores overlap, then you would see a spike in the distribution, 0.5 angstroms.
Yeah, I was trying to think in my head whether that's a bias you want or not. But yeah, thank you very much. Do we have any questions? We've got a question. I'll pass it over to Professor. All right, yeah. If everyone online can hear.
Wondering that the fragments have functionality that doesn't work, and often they have functionality that's away from the protein. Hydrogen bonding functionality. How did you make the fragments? Why did you pick the lateral point contact the surface of the protein? Or did you just use the fragments?
As quite naively used. Well, I guess in this case, you can see some of the fragments don't fit, then bind to the binding site. I only used the ones that were in the binding sites, and I kind of ignored any other interactions that were going on. It's the naive approach, yeah.
Fragments in the body, they have redundant functionality. Might appear as a matter.
That would be left out, yeah.
Does anyone else have any questions? No? In that case, I think we'll wrap up there. Thank you very much, Will. Another round of applause. And just before we go, I'd like to say to everyone online, please stay online, and Andreas will put you into breakout rooms so you can network and meet new people or catch up with old friends. And here we'll all go to the pub. So let's go to the Alma. All right. So thank you very much again to all the speakers.